So now we're ready to talk about derivatives. And so the big looming question is, what in the world is the derivative of a function of more than one variable? Well, let's start with the definition of the derivative of a function of one variable. So f prime of a is equal to the limit as x approaches a of f of x minus f of a divided by x minus a. Okay, and now remember, this has the interpretation of being the slope of the line tangent to f of x at x equals a. So here's our tangent line of our function f of x. So the slope of this line is the derivative of this function. Okay, so what in the world are we going to do with a function of two variables? Well, now we have two different directions to worry about. So if we think about the domain of our function, how are we going to define the derivative at a point a, b? Well, we're going to cheat a little bit. What we're going to do is we're going to instead look at g sub b of x, which is f of x b. So what I'm going to do, if I'm looking for a derivative at the point AB, what I'm going to do is I'm just going to fix the y value. And now what that does is that gives us a function of one variable. And now the domain of that function of one variable is this line y equals b. Now the function is actually living above or below this line right here. But if so we're kind of cutting the function. This is in 3 dimensions, this is going to be a plane, y equals b. And so we're actually getting, so this is a plane y equals b. So here's x, and this is going to be z. We're actually getting a function of one variable when we cut by this plane. So we're fixing a y value, and here's going to be x equals a. And now it makes perfect sense to talk about the tangent line, well, when it exists, and the slope of that tangent line. So what do? Well, notice that this is the function g sub b of x. Okay, and what we're going to do is we're just going to take the derivative, and we're going to call that the partial derivative of f with respect to the variable x. And now there's going to be some interesting notation here. We're going to have this is a delta, but it's kind of a fancy curly delta. So this is read partial f, partial x, partial derivative of f with respect to x. And then of course we're evaluating this at the point AB because we're interested, just like up here, we're looking at the derivative evaluated at A. Here we're looking at the partial derivative evaluated at AB. So that's one way to notate the partial derivative of f. Another way is f sub x of AB. But what is it actually? Well, it's the derivative of this function g sub b of x with respect to x. And notice that I have a dependence on the y point b, and now I'm taking the derivative and evaluating it at a, exactly in the one variable situation. So here's our notation. This will be very important notation later. And for the rest of the class, the partial derivative, and this is what it is. Well, we just plug in this value b, and then we just take the derivative with respect to x. So let's not leave out the variable y. We talked about the partial derivative of a function with respect to x. We can also talk about the partial derivative with respect to y. And this will be denoted partial f, partial y. And now we're evaluating at a point AB. We're going to denote this f sub y of AB. And now it's going to be exactly the same thing, except first we're going to fix our x coordinate to be a, so we're going to fix x, and then we're going to differentiate the new function that's just a function of y, and evaluate that derivative at the point b. Okay, and of course in general we can do this for more variables. We can take the partial derivative with respect to z, we can take the partial derivative with respect to t, or whatever variables, independent variables, our function depends on, we can take the partial derivative with respect to those variables. And so this has a very important interpretation. So the partial derivative with respect to y is the rate of change of f at this point AB in the y direction. And of course the partial derivative with respect to x has the interpretation that's the rate of change of f of xy at AB in the x direction. And we can also just define these functions, f sub x is just partial f, partial x, actually without evaluating at the point for wherever it's defined. So for any fixed y value where the x derivative exists, then we have a partial derivative as a function of x and y. We have the same thing for the partial with respect to y. So these are now functions of x and y. And then we have the same thing if we have a function of three variables, the partial with respect to z. And now the trick to actually finding these partial derivatives is you just treat the other variables as constants and only differentiate the function as a function of one variable with respect to the variable that you're looking for the partial derivative with respect to. So we can also talk about higher derivatives and higher partial derivatives. So if we have f xy is a function of two variables, then we have f xx, and now what is this? This is just partial x of partial f partial x. So you just take the derivative with respect to x twice, keeping y fixed. We also have the second derivative with respect to y. That's not so surprising. But the interesting thing happens when we look at these two functions. So if we look at f x y, this is going to be the partial with respect to y of the partial with respect to x. And then fyx is going to be the partial with respect to x of partial f partial y. Now notice the order here. Here I'm taking the partial derivative with respect to x first, then taking the partial derivative with respect to y. Here I'm taking the partial derivative with respect to y first, then taking the partial with respect to x. And so the question is, are these the same thing? And that's an excellent question, and it turns out to not always be the case. Actually, sometimes if you take the derivative with respect to x first, then y, you get something different than if you take the derivative with respect to y first and then x. But what we do know is that most of the time they are the same. So fyx equals fxy as long as fx, fy, fxy, and fyx are all continuous. So in that case, we have equality. And most of the time, as you've kind of seen in your experience in Calc 1, most functions we deal with are continuous. And most functions we deal with have derivatives that are continuous. So this isn't really a significant requirement. So most of the time, we're going to have that these derivatives, and now these are sometimes called mixed partials. So most of the time, the mixed partials will be equal. So absolutely the biggest takeaway from this partial derivative topic is how to take partial derivatives. So we talked about sort of what they are. They're kind of the slope of the tangent lines of these cross sections of the function. But most importantly right now, we just want to get used to taking partial derivatives and the method of taking partial derivatives. And the key is if you're taking the partial derivative with respect to x, as we're doing first, you just want to treat y as a constant. So f sub x of xy, and notice this is the same thing as what we're looking for, partial f, partial x. I'm going to differentiate the function with respect to x, treating y as if it was just a number, like 2 or 3 or 10 or whatever. So we have a chain rule, so it's going to be 2 times xy plus 1 squared. And then I want to differentiate, not squared, so it was squared. I bring down the 2, and now it's to the first. And then I multiply by the partial derivative of the inside with respect to x, which is, well, this is x times a constant, so the derivative of a constant times x is just equal to that constant. So I can write this as 2y times xy plus 1. Now the partial derivative with respect to y is exactly the same thing, except I want to treat y or x as a constant. I want to treat x as if it was just any old number. And so I do the same thing. I have to bring down the 2 because this is a chain rule. And then I leave the inside alone. And then I multiply by the derivative of the inside, which in this case is just, well, this is constant times y, so the derivative is just the constant that I'm multiplying y by. So in other words, this is 2x times xy plus 1. And these are the two partial derivatives with respect to x and with respect to y of this function. All right, so we're having so much fun, let's do it again. Okay, so let's take the partial derivative of this function with respect to x. So again, I'm just going to treat y as if it's a constant. So y squared is just going to be a constant. So all I'm taking the derivative of is this e to the x squared. So that's going to be e to the x squared times the derivative of x squared, which is 2x, and then times y squared, like that. And notice I'm leaving the constant alone, as if it's just multiplying by a function of x. I'm treating this as a function of x. So I just differentiate the only thing that has to do with x, which is e to the x squared. So I can write this as 2xy squared e to the x squared. I want to kind of clean it up a little bit. And now the partial derivative with respect to y, I just want to leave that e to the x squared alone, because now that's a constant, because I'm fixing x. I'm treating x as if it were a constant. So what do I have? I just have e to the x squared, that constant, times the derivative of y squared, which is 2y. So there is my partial derivative with respect to y. Here's my partial derivative with respect to x. All right, so here I want to find the second partial derivatives. The second partial derivative with respect to x, the second with respect to y, and the second with respect to z. And so the way we do that is we start by taking the first partial derivative. Surprise, surprise. So fx of xyz, well, I'm just going to take the derivative with respect to x. Well, this function is just sine of some stuff. So the derivative is going to be cosine of that same stuff. And then I'm going to multiply by the derivative of what was inside with respect to x. That's crucial. So the derivative of what's inside, now I'm treating y and z as constants. So y times z, the derivative is 0. The derivative of xz is z, and the derivative of xy is y. So I'm going to get y plus z. Excellent. So now I'm ready to take the partial derivative of this function with respect to x, which is the second partial derivative of the original function with respect to x. So I'm going to do the same thing. Now notice that this is not a product rule because this function doesn't depend on x. This is just a constant. It's like 2 plus 3. In this case, it's just y plus z. So we take the derivative of this function, which is negative sine, and then we leave the inside alone. And then we're going to multiply by the derivative of the inside with respect to x, but we already know what that is. That's y plus c. And then I have this other factor of y plus c from the first derivative. So this is actually y plus c squared. And it's very easy to see that fyy is almost exactly the same thing because the procedure is the same. Actually, this function is symmetric in its variables, except instead of multiplying by the derivative of the inside with respect to x squared, it's going to be the derivative of the inside with respect to y, which is going to be x plus c. And then fzz is going to be exactly the same thing, except I'm going to multiply by the derivative of the inside with respect to z squared, which is going to be x plus y squared. And there we are. All right, so here we want to take some more partial derivatives. So let's start with fxx. So we'll take the partial derivative with respect to x first, which, okay, this c we're going to treat as a constant, and y we're going to treat as a constant. So this is just x over constant plus constant. The derivative is just going to be 1 over y, like that. Because this is just 1 over y times x, which is a constant times x, so the derivative with respect to x is just that constant, 1 over y. And so f(x)(x), we're going to take the derivative of this function with respect to x, but this is just a constant with respect to x, so it's just 0. Okay, and then we can go on to y. And now this is going to be a little bit trickier because this is x over y. So the x I'm treating as a constant. So I'm really taking the derivative of 1 over y, which is negative 1 over y squared. But I have this factor of x on top. That's just a constant. And then the derivative of z with respect to y is, again, 0. So if I take the derivative again with respect to y, well then I'm going to just take the derivative of 1 over y squared, which is going to be negative 2 over y cubed. So we're going to be left with 2x divided by y cubed, like that. Very good. And now finally, with respect to z, well, this x over y is a constant. So when I take the derivative with respect to z, it goes away. It's 0. And then the derivative of z is just 1. And now when I take the derivative again with respect to z, the derivative of 1 with respect to any variable, in this case z, is just 0. So there are our double partial derivatives. All right, so this is a really interesting problem because what we want to do is actually verify that for this particular function, it doesn't matter whether we take the derivative with respect to x or y first in the mixed partial derivatives. Now we said that most of the time this is going to be the case, but it's super cool to actually see it in practice. So let's just start taking derivatives. So the partial with respect to x of this function, well, this is going to be a chain rule. So we have 2, and then the derivative of square root of something is 1 over 2 times the square root of that something. And then we use the chain rule. So we multiply by the derivative of the inside with respect to x, which y squared is just a constant, so we just get 1. Or in other words, this is just 1 over square root of x plus y squared. Okay, and now the derivative of this function with respect to y is very similar. So we have 2, and then we're taking the derivative of the square root of this guy. So it's 2 square root of x plus y squared. And then now by the chain rule, we're multiplying by the derivative of the inside with respect to y. So the derivative is just 2y, like that. All right. So in other words, this is just 2y over square root of x plus y squared. Okay, so now let's take the derivative with respect to x and take the derivative with respect to y. All right, so we want to take the derivative of this function. Now this function is just x plus y squared to the negative 1/2. So the derivative is negative 1/2 x plus y squared to the negative 3/2 times the derivative of the inside with respect to y, which is just 2y. Or in other words, the 1/2 cancels with the 2, and we have negative y over x plus y squared to the 3/2. Now let's take the derivative of f sub y with respect to x. So we're going to take the derivative of this with respect to x. But notice that this is just 2y times x plus y squared to the negative 1/2. So the derivative with respect to x, this is just a constant. So we have 2y times, we bring down the negative 1/2, and then we have x plus y squared to the negative 1/2, and then we multiply by the derivative of the inside with respect to x, which is just 1. Now look at this. The 1/2 cancels with the 2, and that's 3/2, sorry. Bring down the negative 1/2 and subtract 1. And what are we left with? Negative y over x plus y squared to the 3/2, which is exactly the same thing as we got when we took the derivative with respect to x first and then y. Amazing. So whoa, you look at this function and you say, oh my gosh, I have to take the derivative with respect to x and then y of this mess. Well, let me take the derivative with respect to x first. What do I get? Derivative of xy with respect to x is just going to be y. And then, oh my gosh, I could use the chain rule 500 times here. This is going to be 1 over square. No. Don't do that. Okay, so why do I say don't do that? Well, if I take the derivative of this function with respect to x first, we are going to get an absolute mess. And I would never want anybody to do that. Not even my worst enemy. But what would happen if I take the derivative with respect to y first? Well, notice what happens. This crazy complicated function over here does not depend on y. It only depends on x. So this is a constant. So the derivative with respect to y is just x. Because I take the derivative here, x is a constant. Derivative of a constant times y is x plus 0. Then I can take the derivative with respect to x, and I get 1. Now wait a minute, this is not answering the question that this asks for. It says compute f(x,y). So take the derivative with respect to x, and then take the derivative with respect to y. But here, I've taken the derivative of y with the derivative of f with respect to y, and then with respect to x. But these are the same. I told you that most of the time these are going to be the same, as long as the partial derivatives are continuous. But I can just see that this is an algebraic function. So it is a continuous function, and any of its derivatives are going to be continuous wherever they're defined. So therefore, this function here is going to be equal, this derivative of y, then the derivative with respect to x is going to equal what we're looking for, which is 1 in this case.